colleagues, discuss electrophilic aromatic substitution reactions to do with heterocyclopentadienes. Okay, so let's break down this word into small units that we can understand. So hetero means there is presence of a heteroatom. So we have a heteroatom present. Cyclo means it's cyclic. So the molecules in question are cyclic. Pent will be what we use for 5 members. So as we know, pentane contains 5 carbons. So pent will symbolize 5-membered ring. So this is a 5-membered ring. And dienes means it has 2, of course, 2 double bonds. So the di means 2, and then the ins is symbolizing the 2 double bonds. So this is the meaning of these heterocyclopentadienes, and as we can see depicted on this table, on this board, we have 3 structures that are referred to as heterocyclopentadienes. We have pyro, we have furan, and we have thiophene. Okay, so these 3 molecules are what we're calling heterocyclopentadienes, which are able to undergo electrophilic aromatic substitution reaction. Okay, so in reference to reactivity, as we can see, these heterocyclopentadienes are actually competitively more reactive as compared to our benzene. So benzene is an aromatic compound that we've previously looked at as an aromatic example. So not only benzene is an aromatic compound, we have aromatic compounds that have heteroatoms. So these aromatic compounds are referred to as heterocyclopentadienes. And as we can see, the reactivity of these heterocyclopentadienes starts from the greatest reactivity, which is pyro, and then we have furan, and then we have thiophene. Lastly, but not the least, we have benzene as the most least reactive on this chart. So if we compare benzene's reactivity to the reactivity of the heterocyclopentadiene, we'll conclude to say heterocyclopentadienes are more reactive in electrophilic aromatic substitution reaction than benzene. Why do we say so? Okay, so this is due to the fact that the intermediate produced by this heterocyclopentadiene will be more stable as compared to the intermediate produced by a benzene ring. Okay, so in case we attach an electrophile to our benzene atom at this carbon here, we'll notice to say this bond will break, okay, and will form a positive charge on this carbon right there. So as we can see, there is a positive charge within the ring which cannot be further stabilized by any of the pi bonds. Only resonance is able to take place within this structure. But if we try to do the same thing to these heterocyclopentadienes, of which I'll pick one, I'll use pyro. So if we try to attach an electrophile to pyro on this carbon right here, we discover to say the intermediate are produced. So this is our electrophile. The intermediate produced after this bond breaks is able to be stabilized by the heteroatom. So the heteroatom has a lone pair. As we can see, there are some lone pairs on these heteroatoms. So these heteroatoms are able now to resonate within the ring and are able to form a more stable intermediate as compared to a plain benzene ring. So that's why their reactivity is relatively much competitive as compared to the benzene ring. So with those points in check, let's go further and look at some electrophilic aromatic substitution reactions involving these molecules. So our first molecule of choice will be furan. We'll use furan for the following reactions. Okay, so we want to see the reactivity or how they are able to undergo electrophilic aromatic substitution reactions. So furan is a 5-membered ring, as the name suggests, and it consists of oxygen as the heteroatom. Oxygen has 2 lone pairs, so we have to indicate lone pairs always. Alright, so this is our furan molecule. Okay, so let's undergo electrophilic aromatic substitution reactions on this plain furan ring. So it's unsubstituted, that means it has no other substituent groups attached. So let's try to halogenate this ring. So we'll undergo halogenation of this ring. I'll write a complete equation of halogenation, of which I'll use chlorine as my halogen. Okay, we want to see the properties of the reactions of these heterocyclopentadienes. Okay, so these are aromatic compounds, that means they obey the aromatic criteria. So if we were to do an electrophilic aromatic substitution reaction, we would observe the 3 steps. So we would want an aromatic electrophile generation, an aromatic attack, and want to restore aromaticity, because these are aromatic compounds. So in the form of, in the case of halogenation, where I'm using chlorine in this case, so I'll use Cl2, and then as my catalyst I'll use iron tetrachloride. Okay, so the products we are to get are as follows. So this will be our furan. Okay, then these are our dienes, which are our 2 double bonds, and we have our substituent or incoming group, which is the chlorine. Then plus the lowest base we had utilized, the iron tetrachloride, and hydrochloric acid as a byproduct. So this is the complete equation or the complete reaction of halogenation using chlorine of this heterocyclopentadiene. Okay, and this is the product. One might ask, what criteria are we using to identify the location of the incoming molecule? Good question. I like that one. So I want to explain the positioning of the incoming molecule in a heterocyclopentadiene ring. So let's take note of this complete equation. Before we start the mechanism, I would like us to include a step that I'd like to call analysis, where we analyze why we are choosing this position for the incoming molecule. Okay. Alright. So this is our unsubstituted heterocyclopentadiene ring. As we can see, it possesses a conjugated system. So in this system here, we'll try out these various positions, being one. So if this is the first position, this should be C2, carbon 2, carbon 3, carbon 4, and carbon 5. So let us number these carbons in that order. Of course, if you are starting from this direction, this will be your carbon 2, carbon 3, carbon 4, carbon 5, and so on. Alright, so after numbering, we want to understand the properties of an unsubstituted heterocyclopentadiene ring. So one of the properties is that if it's unsubstituted, it has a symmetry. Okay, so this is what we mean by symmetry. It's symmetrical, so that means the left side is equal to the right side. So when we have this property, we mean that this carbon number 2 here is going to have the same properties as this carbon number 5. Okay, so in an unsubstituted heterocyclopentadiene ring, carbon number 2 is equals to carbon number 5. Carbon number 4 is equals to carbon number 3. This is a property I want you to keep at the back of your head. We utilize it in an unsubstituted heterocyclopentadiene ring. Alright, so keeping that in check, we would want, we want to know which position would be most suitable for the incoming molecule. So we see we only have two actual positions in this case, which is this first position here and this second position here. If we have equalized these two and these two based on symmetry, that means this and this are the same, so this is 1, and this are the same, so they are also 1. Right, so with that in check, let's do some resonance. So in this analysis step, we utilize resonance. Okay, so analysis. In this analysis step, we utilize resonance. So we'll attach an electrophile on this carbon and look at its resulting resonance intermediates, and then we'll do the same for this position to see its resulting resonance intermediates, and then from there we are able to have a conclusion on the direction of the incoming molecule. All right. Okay, so all right. It's a code there. Okay, so we'll start with carbon number 2. So on carbon number 2, we'll react with our electrophile and we'll see the resonance as follows. So if we attack carbon number 2, let's observe the movement of the double bonds and the lone pairs within the ring. So if carbon number 2 is attacked, which is this position, this double bond will break. So this new bond will be formed between carbon number 2 and the incoming electrophile. So we have our electrophile here, and then we have this bond broken, so there's a positive charge on this carbon right here, and then the other pi bond is maintained because there's no reaction. So this being our first resonance intermediate, the positive charge within this structure is able to resonate within the ring. So we see that the adjacent pi bonds are able to stabilize the positive charge. So upon stabilization of this positive charge, we're leaving a deficiency of electrons on this carbon. So we have our second resonance intermediate. So this is our oxygen. Let's always indicate the lone pairs. They are quite cardinal in these reactions. So if this stabilization occurs, there's a new solid bond formed on this position, and there's a positive charge generated on this position. So this is our second resonance intermediate. From this position, we use our lone pairs because we don't have any other adjacent pi bonds. We utilize the lone pairs adjacent. They also have the ability to stabilize a positive charge. So upon stabilizing of this positive charge, we'll have to realize another pi bond there. Okay, so we have this happening. So we have our new pi bond. Okay, keep in mind oxygen has lost a lone pair, so oxygen is now possessing a positive charge. Okay, there's a new pi bond between oxygen and the adjacent carbon. Okay, and then the already existing pi bond right there. Okay, this is our electrophile here. Right, so that is the resonance intermediate. Okay, so if we look at this positive charge, it can't resonate further, so that means this is the final resonance intermediate. So let's take note of the movement of this positive charge, and as we can see on the movement of this positive charge, it's able to form 3 intermediates. So let's take note of the 3 intermediates. Okay, so this is the first resonance at carbon number 2. Let's look at the second resonance at carbon number 3 and look at the relative stability between the two resonance structures. Okay, so if we ought to attack carbon number 3, that means this carbon will be the one involved in the new bond and will realize such a molecule. So this is our furan still. So we've attacked this carbon here, so this pi bond has to break. So we are forming a new bond between carbon number 3 and our electrophile. And then there's a positive charge on this carbon. We maintain this pi bond because there is no reaction. So this is our first resonance intermediate. So this resonance intermediate is also having the capability of resonating within itself and forming other resonance intermediates. So adjacent to this positive charge, we see there's a lone pair system. So we utilize this lone pair to stabilize this positive charge. So in using this lone pair, oxygen then loses a lone pair, so it gets a positive charge as a result. And then after forming this bond here, we lose this positive charge within the ring and form a solid pi bond between oxygen and the adjacent carbon. We maintain the other pi bonds. We have our electrophile here. So as we can see, the positive charge can be stabilized further. This is the last of the resonance structures on furan. If we attack on carbon number 3, so let's look at the total of the resonance structures. 1, 2. So we only have 2 total resonance structures. That is good, because in the first reaction where we had used carbon number 2, we had realized 3 resonance structures. What does this information tell us? This information gives us the relative stability. So 3, which has the highest resonance structures, is the most stable. Okay, so carbon number 2 here, which had 3 resonance structures, is the most stable. So that means carbon number 2 is the likely position for the incoming molecule, because it's able to form more stable intermediates as compared to carbon number 3. So the more resonance a position is able to form, the more stable the position is, and the more likely the incoming molecule to attack that position, as we have just experimented and we have seen with our own eyes. So without further ado, let's do a complete mechanism on the halogenation of furan. Okay, so this is our furan. Let's write the full equation. This is our furan molecule, which is able to undergo halogenation. I'll use chlorine as my halogen, and we'll use iron tetrachloride as our Lewis acid products formed. Now we know the position that is the most likely to be occupied. So we know it's this position here. So the chlorine will be here, and then we have this as our product, plus our hydrochloric acid and our Lewis acid, which is our catalyst. It remains unchanged throughout the reaction. So this is our overall reaction. We always write it as the first step, but let's look at the step-by-step mechanism of this reaction. Okay, so we'll attack step 1. So on step 1, we'll deal with electrophile generation. So we have to generate an electrophile, of which If you haven't watched the previous videos on these steps, please kindly revisit them. They are quite cardinal, but I'll run through as quick as possible. But I know you'll be able to refer if you have any questions. Alright, so the first step is always electrophile generation, where we have our chlorine atoms. So these chlorine atoms react with the Lewis base, which is the iron tetrachloride, where one chlorine gives out a lone pair, where we produce a catalytic complex. Okay, we produce a catalytic complex, positive charge on chlorine, iron. Iron possesses a negative charge, and tetrachloride. Okay, so this catalytic complex is relatively unstable because chlorine is electronegative, as we have established. So chlorine will tend to break its bond with the other chlorine to stabilize this positive charge it has. So this means there will be cleavage here, and as a result of this cleavage, we produce a chlorine atom that has lost an electron. So we produce a positively charged chlorine atom. This is our electrophile, plus this molecule here, chlorine iron tetrachloride, where the iron is relatively negative charged as our conjugate base. These are the results of the first reaction. So let's look at the second step, which is aromatic attack, where we use this newly generated electrophile. At this stage, we attack the aromatic ring. So the aromatic ring in our case is furan. So furan is a 5-membered heterocyclic ring. Okay. So we attack furan. So this electrophile is able to abstract the pi bonds. Preferably, we use this carbon because we see it's the most stable. It's able to form the most stable product, as we've seen through the resonance. So this pi bond right here will stabilize that positive charge on that electrophile to produce the following intermediate. Okay, so this bond will break, then we produce a positive charge here, chlorine atom here. Okay, that is our intermediate. We can do resonance further, where this pi bond tries to stabilize the positive charge, and we're able to realize the following molecules. Bear with me, colleagues, on the space. I'll have to rub some of the materials on top, so let's follow closely. So as this stabilizes, as the pi bond stabilizes a positive charge, we result into a stable or a solid pi bond on that position. So we'll have our oxygen there. Okay. Right, so we'll form the positive charge here. So we have a positive charge here. And then we have our chlorine atom here. And then we have our oxygen atom at the base. It is unchanged. So as a result of that resonance, we have a positive charge at this position. Okay. So this positive charge here can further be stabilized by the lone pair on oxygen. So oxygen is able to stabilize this adjacent positive charge, giving us our third resonance, okay, which is showing as follows. So this would be our third resonance. So if oxygen loses a lone pair, that means it gets a positive charge, and it forms a solid pi bond between itself and the adjacent carbon. So there's a solid pi bond here. And then we maintain the previously formed pi bond, and this is our last intermediate, because the positive charge can't resonate further. Alright, so from this information, we can deduce our resonance structures and our uranium ion respectively. So the uranium ion will depict the movement of the positive charge within the ring. So the positive charge has begun from here and has resonated to this position and finally to this position. So that means the resonance starts from here and it ends here. So if we're looking at our uranium ion, in case we've been asked to present with an uranium ion, we look at the migration of the positive charge within the ring. So the positive charge moved from this carbon to this carbon and this carbon, so that means we have resonance coming in this direction. Okay, so this is a positive charge. That is our resonance, ladies and gentlemen. So with this information, we can further look at the final step, which is step 3, where we have to restore the aromatic properties of this ring. So we'll look at restoration of aromaticity. At this stage, we'll use the first intermediate of step 2, which is this atom here. So this is our oxygen molecule. Okay. So oxygen is having 2 lone pairs which have to be indicated, and attack happened on carbon number 2. So we have chlorine here. pi bond within the ring. So there will be a pi bond formed as a result of these electrons stabilizing the charge. Let me draw the final products of this reaction. So I'll erase these and then we'll indicate a section for products. So these are the products of the reaction. So these are our products. So we have our heterocyclic ring whose aromaticity has been restored. We have our newly formed pi bond at this position here. So we have a pi bond here. And then we have our attached molecule chlorine. And then already existing pi bond on this position. Okay. So this will be our major product of the reaction. And accompanied to this, we had produced some hydrochloric acid as our byproduct. And we had also realized back our catalyst, which is iron tetrachloride. So these are the products of the halogenation using chlorine of furan.